Last section of the book continues on with hypothesis testing, except now we look at it for when we're doing proportions instead of means. So the first hypothesis test here on your classwork sheet tells me a college statistics department believes that the pass rate in the intro statistics class should be 85%. They want a test to make sure their classes are not too hard or too easy. Over the past 2 years, 350 students have taken the class and 280 have passed. Conduct a test of hypothesis whether this proportion is different from 0.85 at the 0.05 level of significance. First thing I have to do is find my null and alternative. HO, HA. It says conduct a test of hypothesis whether the proportion is different from 0.85. Different from 0.85 doesn't say less than or more than, so it's a not equal to test. Not equal to 0.85, and I'm going to use P as the population value for proportion. That means that my null is that P does equal 0.85. Next thing I'm going to do is pull out the key numbers in here. So we have 0.85 as the population value for P. We need to find what the sample value is, but in order to do that, we need N, the number of people they looked at, which is 350, and we need X, the number of people who fit, which is 280. That allows us to find P hat, which is 280 over 350. That should give me 0.8. Then we need to see what the confidence level is. Here they gave it as a level of significance, not confidence, so I can just plug that straight in as alpha. Now that I have the key information, I can set up my z-score formula. The z-score formula here for proportions is z equals p hat minus p over the root of p 1 minus p over n. Key note here is in bottom, I'm using the hypothesized p, not the sample p. So when you did confidence intervals, this all used p hat or the sample p. It's because we didn't have a hypothesized p to go off of. When we do z-scores, we want to make sure this bottom is based off the hypothesis, not off the sample value. So here my test statistic becomes z equals 0.8 minus 0.85 divided by the root of 0.8, 1 minus 0.8 over 350. I'm going to get out my calculator, put in parentheses 0.8 minus 0.85 and parentheses divided by new parentheses root, new parentheses 0.8 end parentheses 1 minus 0.8 end parentheses divided by 350, making sure everything's still all under the root, and then I can close that final parentheses. When I put this all in, I get negative 2.338, which I'm going to round to negative 2.34. If you're getting something different than that when you put this in your calculator, it's probably something to do with the parentheses on bottom, making sure this 350 is also under the root. When I go to the negative side of my table and look up negative 2.3, and then I go over to 4, I get 0.0096. So far we've got the null and alternative step 1. We've got the test statistics step 2. We're now looking for the p-value of the test. This p is not the p-value of the test. It's basically something I can use to find the overall p-value by looking back at the alternative hypothesis. If the alternative had been a less than alternative hypothesis, this would be the p-value. Because it's not equal to, we have to consider if it's a left or right-sided value. In this case, it's negative or a left-sided value. So when we have a not equal to with a negative z-score, we take the p-value times 2 to get the test probability. So 2 times 0.0096 is going to give me 0.0192. Now that I have the test probability, I can compare it to alpha, 0.0192, which is the test probability, versus 0.05, which was our given level of significance, or alpha. In this case, alpha is greater than my test probability, which means my conclusion is reject the null. So what I've done is I've proven at the 0.05 level of significance that a number different from 85% passed the Intro to Statistics class.